Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research. From advanced biomedical technologies to breakthroughs in AI, materials science, chemistry, and physics, all told is because, making a blue LED was historically so notoriously difficult that the scientists who finally figured it out back in the day actually won a Nobel Prize for it.
Yeah, they did.
Mm.
Red and green were relatively easy to figure out, but blue was just a total nightmare.
And today, we are looking at the next generation of that exact same problem. We are taking a deep dive into a brand new paper published in the journal Nature.
This is a really exciting one.
It is. Our mission for this deep dive is to uncover the future of high-definition screens, which relies on this cutting-edge material called Perovskite LEDs, or PeLEDs for short.
It's such a fascinating scientific journey. We're going to look at why creating a pure, stable blue light using these advanced perovskite materials has been so incredibly difficult for researchers around the globe.
Right.
And how they finally got past a barrier that, honestly, many thought was physically impossible.
So here is the central mystery we are going to explore with you today. Why is cracking the code for this pure blue light so incredibly hard? And how did a team of scientists finally solve it using something called isomeric multi-hydrogen bonding?
Which is quite a mouthful.
It is, yeah. I'll give you a hint right now, though. It basically involves chemical twins essentially linking arms to force a chaotic system into order.
I like that visual.
But we aren't going to reveal exactly how that molecular hand-holding works just yet. Let's start with the baseline.
Okay.
If you're listening to this and thinking, why do we even need a new screen technology? Like, why not just use the OLED screens we already have on our phones and TVs? What is the actual advantage here?
Well, it really comes down to manufacturing scale and cost.
Okay.
Metal halide perovskites, or MHPs, are basically considered the holy grail for next-generation displays because of a property called facile solution processability.
Which means what, exactly?
So traditional silicon, or standard OLEDs, require these incredibly expensive, high-vacuum, high-temperature manufacturing environments. You need multi-billion-dollar fabrication plants just to keep the environment perfectly sterile and pressurized.
Right, like those massive clean rooms where everyone wears those full-body bunny suits.
Exactly. But perovskites are totally different. They can be processed at much lower temperatures directly from a liquid solution.
So meaning you can basically print them?
Precisely. You can envision a future where high-definition screens are essentially printed on a massive scale, almost like a newspaper press.
Oh, wow.
Yeah, which would drive down the cost of consumer electronics dramatically. And on top of that, perovskites offer this incredible color purity and tunable band gaps.
Tunable band gaps?
Yeah, so you can dial in the exact vibrant shade of color you want. And the industry has already had massive success here. Like red and green perovskite LEDs are already performing amazingly well in the lab.
Right, but then we hit this massive roadblock when we try to make them glow blue. Specifically, pure and deep blue light, which operates at a wavelength between 455 nanometers and 470 nanometers.
Yeah, that's the tricky spot.
Why is this specific color acting like the problem child of the perovskite family?
Well, it's purely an issue of energy demands. As we know, blue light has a shorter wavelength and requires much higher energy than red or green light.
Makes sense.
So in a semiconductor material like a perovskite, to get that high-energy blue photon to actually emit, the material requires a wider band gap.
And to push electrons across that wider band gap, you have to pump more energy into the system. You have to crank up the driving voltage, right?
That is exactly where the physics clashes with the chemistry.
Uh-oh.
Yeah, metal halide perovskites have a specific ionic crystal structure, known as an octahedral structure. It is highly conductive and great for color, but structurally, it's somewhat fragile. So you have this delicate crystalline framework, and suddenly you are forcing a massive amount of high-voltage electrical energy through it just to clear that wide band gap and get that blue color.
I was actually trying to visualize this when looking through the source material, and I came up with an analogy. Let's compare this to an engine.
Let's hear it.
If you want a car engine to hit a super high-pitched, screaming RPM, which is our blue light in this scenario, you have to pump it full of high-octane fuel and just press the pedal to the metal.
Right.
That's our high driving voltage. But these perovskite crystals, because of that fragile octahedral structure, are like an engine made out of brittle ceramic instead of solid steel. Am I getting that right?
That is a phenomenal way to picture it.
Because it seems like pumping them with that much high voltage is like revving that fragile ceramic engine so hard and so fast that it literally vibrates itself to pieces.
Yeah, exactly. When you rev that perovskite engine too hard, the material physically degrades. The technical term for this is phase segregation and ion migration. Because it's an ionic lattice, the intense electric field literally starts ripping the charged particles, the ions, out of their designated positions.
Oh, man.
Yeah, the octahedral framework twists, deforms, and eventually just falls apart. The light shifts from a pure, sharp blue to this muddy sky blue. The efficiency drops off a cliff, and the device dies.
Wow.
To give you some context, in the control test they ran for this study, a standard blue PeLED died in just 50 minutes.
50 minutes. I mean, you can't exactly sell a TV or a VR headset that burns out in less than an hour.
Definitely not.
So scientists obviously knew this high voltage destruction was a huge problem. What were the early workarounds? Like, what did people originally try to do to fix this?
So the initial prevailing strategy was focused on changing the physical size of the crystals.
Okay.
Scientists thought, well, if the bulk material falls apart at high voltage, let's shrink the perovskite crystals down into tiny low-dimensional structures like quantum dots.
Oh, quantum dots. I've heard of those.
Yeah. When you shrink materials down to the nanoscale, quantum mechanics takes over, and you can naturally widen the band gap without needing to pump in quite as much destructive voltage.
Wait, hold on, though. If you shrink them down to the nanoscale, don't you have to protect them?
You do.
Because you can't just have raw quantum dots floating around reacting with everything. Doesn't adding a protective chemical shell basically act like an insulator and ruin the electrical flow?
You hit the nail on the head. That is exactly why the quantum dot approach stalled out.
I see.
To keep those tiny crystals stable, you have to wrap them in organic molecules called ligands. But those bulky organic ligands act as electrical insulators.
Right.
They destroy the material's carrier mobility. Electrons just can't flow smoothly from one quantum dot to the next because these massive chemical shells are in the way.
So scientists were totally trapped in this paradox. If you shrink the crystals to get the blue color safely, you have to wrap them in insulation and they lose all their electrical power and efficiency. But if you keep the crystals large and turn up the voltage to get the power, they literally self-destruct and migrate apart.
Exactly.
How did anyone solve this? This sounds like a physical impossibility.
It really does. Which is why this new research is so groundbreaking. It requires shifting our perspective entirely. Instead of trying to alter the macro-level structure of the crystal or shrinking it down, what if you could fundamentally change how the crystal holds itself together from the inside out?
Which brings us to the heroes of our story. This breakthrough comes from a research team led by Dr. Yuanzi Wang, Dr. Xuyang Yang, and their colleagues from Shanghai University, along with researchers from several other institutions.
A fantastic team.
Yeah, and their findings were just published in the prestigious journal Nature. Their solution involves introducing what they call isomeric molecules.
Yes. Isomers are molecules that have the exact same chemical formula the same number of atoms of each element. But those atoms are arranged differently in three-dimensional space.
So they're chemical twins.
They are chemical twins. And the team used two specific twins for this experiment. OBCI, which is O-benzyl hydroxylamine hydrochloride.
Wow.
I know. And NBCI, which is N-benzyl hydroxylamine hydrochloride.
Okay, I am definitely not going to try to memorize O-benzyl hydroxylamine hydrochloride.
So for the sake of our listeners, we're just going to call them the O-twin and the N-twin.
That sounds like a good plan.
Because from what I understand, it's not just about what these chemicals are, it is all about exactly where they place them in the device, right?
Exactly. The architecture is everything here. A perovskite LED is built in layers.
Okay.
Beneath the actual perovskite emitter layer, which is where the light is generated, there is a foundation called a hole transport layer. Now, in electronics, a hole is simply a positive charge carrier.
Right.
You need positive holes and negative electrons to meet inside the perovskite layer to create light.
Okay, let's go back to visualizing this because I want to make sure I'm tracking.
Oh,
let's imagine the perovskite crystal is like a chaotic, packed dance floor.
Okay, I can see that. The researchers took the first twin, the O-twin, and placed it right at the entrance to the club on that whole transport foundation. The O-twin is acting like a bouncer at the door.
That's a great analogy.
And the paper notes that this O-twin has a very large dipole moment. Basically, it has a strong electromagnetic pull.
Yes, it does.
So, because this bouncer is sitting at the foundation with this huge pull, it sucks those positive electrical charges, the holes, into the club, perfectly balancing the electrical flow.
That handles the first major issue. Imbalanced charge transport. Historically, blue PLs have had too many electrons and not enough holes.
Ah, gotcha.
Your bouncer at the door pulls in more positive charges, creating a balanced, highly efficient environment for light emission. But, we still have to deal with the vibrating, exploding engine problem.
Right.
How do we keep the crystal stable under high voltage?
And that brings us to the second twin, the N-twin. While the O-twin is stationed at the door, the N-twin is mixed directly inside the perovskite material itself.
Right.
It's like a bouncer out in the middle of the chaotic dance floor.
And here is the true aha moment of the entire study. These two isomeric twins, the one at the foundation, the one inside the structure, have functional chemical groups that naturally want to interact.
Oh, really?
Yeah. The O-twin has an oxygen base group, and the N-twin has nitrogen and oxygen groups. When they're in proximity, they reach across that interface layer and form hydrogen bonds.
They literally link arms.
They form strong hydrogen bonds, specifically NH2O bonds, with each other. But it's not just a single connection.
Because there's a bunch of them.
Well, because the N-twin has dual bonding sites. It doesn't just link arms with its twin at the bottom. It reaches its other arm up and bonds directly with the fragile, inorganic framework of the perovskite itself.
That is so cool.
It forms this continuous interlocking network of hydrogen bonds from the foundation all the way up through the entire crystal.
So it creates an invisible molecular level scaffolding. And this molecular arm linking does something completely incredible to the physical shape of the crystal. Normally, when you grow these perovskite films, the crystals just form randomly, right? They look like a jumbled mess of blocks facing all different directions.
Right, a total mess.
But because the O-twin bouncers at the bottom prefer a very specific alignment, and because they are linking arms with the N-twin bouncers inside the crowd, it forces the entire perovskite crystal to grow perfectly straight up.
Which is amazing.
Yeah.
In crystallography, they refer to this as achieving a vertical preferential orientation along the 110 crystal plane.
Hold on, let's pause there. Vertical preferential orientation along the 110 crystal plane sounds very impressive in a Nature paper, but what does that actually mean for the electrical flow? Why does the 110 plane matter?
Well, think about trying to drive across a city. In a normal perovskite crystal, it's a chaotic, isotropic jumble. The crystal grains are facing every which way. It's like trying to navigate a maze of winding dirt roads, dead ends, and sharp turns. Electrons are constantly bumping into misaligned crystal walls, which slows them down and generates waste heat.
But when the researchers forced the crystal to align along the 110 plane, they essentially bulldozed the maze and paved a straight, multi-lane superhighway perfectly perpendicular to the electrodes.
That is exactly it.
Yeah.
The electrical charges can now flow directly through the material with almost zero resistance. It drastically improves the carrier mobility.
Wow.
So they solve the insulation problem that the quantum dot method suffered from without having to actually shrink the crystal.
And it solves the exploding engine problem, too, because that network of hydrogen bonds, that twin arm linking, locks the fragile octahedral structure in place.
Yes.
The ions are anchored. You can finally pump that high-voltage energy into the crystal to get your deep blue light, and the ions physically cannot migrate out of position. The structure doesn't vibrate to pieces because it is tightly bound by this invisible scaffolding.
Which brings us to the actual performance metrics of the paper. We understand the mechanism now, the balanced electrical charges, the vertical crystal highway, and the locked-in structural stability. But how does that translate to real-world performance?
Right. So if they actually managed to build this molecular scaffolding without ruining the conductivity, how did it perform when they actually flipped the switch?
The results are pretty amazing.
Let's look at the stats because they are staggering. Let's start with efficiency, which is measured in EQE, or external quantum efficiency. The control device, so the standard one without the twin molecules linking arms, had a measly EQE of 5.7%.
Just 5.7.
Yeah. But the target device with the scaffolding, it skyrocketed to a record-breaking 22.0% for pure blue at 468 nanometers. And even when they pushed it even harder to an even deeper blue at 463 nanometers, it hit 16.8%.
We really have to emphasize that jumping from under 6% to 22% in material science is not just some incremental standard update. That is a generational leap. And the reason for that massive jump goes right back to that 1 in 10 crystal plane highway we just talked about.
Right.
Because the electrons aren't crashing into misaligned walls, almost all of that electrical energy is being successfully converted into light, rather than being lost as heat.
That makes total sense.
And that efficiency translates directly to brightness.
Oh man, the brightness numbers are wild. Luminance jumped nearly 8 times. The control device tapped out at 371 candelas per square meter.
Okay.
The target device hit 2,902 candelas per square meter. I mean, it is blindingly bright compared to the baseline.
It's a huge difference. But as we noted earlier, power and brightness mean absolutely nothing if the device destroys itself in under an hour.
Right.
You can't put that in a consumer product. The most critical metric in this entire study is the device stability, or its half-life, which we call T50.
Right. The time it takes for the light to degrade to half its original brightness under constant stress. The control device died in 50 minutes.
So how long did the arm-linking twins manage to hold a crystal together? Under the exact same intense stress testing, the target device lasted for 670 minutes.
That is more than 13 times longer.
I know, it's incredible. And perhaps even more importantly than the lifespan itself, there was zero color shifting.
Wait, really? None at all?
None. Remember how the fragile engine would vibrate and the color would shift from pure blue to a muddy sky blue because the ions were moving?
Yeah.
Well, because the ions were locked firmly in place by those hydrogen bonds, the color remained absolutely pure and stable for the entire duration of the test. The entirely halted phase segregation and ionic migration.
That is just brilliant. Okay, so what does this all actually mean for you listening to this right now? Why should you, as a consumer or a tech enthusiast, care about isomeric multi-hydrogen bonding?
Well, if we zoom out to the big picture, this isn't just a cool chemistry trick in a lab in Shanghai. This was the missing puzzle piece for commercializing full-color, high-definition Perovskite LED displays.
Right, because if you want to make a TV, a smartphone, or a VR headset, you need red, green, and blue pixels. We already had highly efficient red and green perovskites.
Exactly.
But you can't sell a display if the blue pixels are dim, require massive amounts of battery power to operate, and die in a month. Because blue is the ultimate bottleneck, solving it means we are now significantly closer to a completely new era of screen technology.
We are talking about screens that are ultra-thin, highly vibrant, and much, much cheaper to manufacture than current OLED screens.
Yeah.
Because these perovskites are solution processable, as we discussed, you can envision a future where high-definition screens are just printed on a massive scale.
It's going to change everything.
It really is. Furthermore, the incredible color purity and tunable band gaps of perovskites mean that AR and VR headsets will be able to achieve a level of visual realism, brightness, and pixel density that currently feels like science fiction.
And beyond just the tech gadgets, I want to point out the brilliance of the scientific paradigm shift here. The researchers prove that you don't necessarily have to discover an entirely new, magical bulk material to solve a structural problem.
That's a great point.
By using invisible molecular-level scaffolding, these hydrogen-bonded networks, they proved you can dictate macro-level crystal stability and electrical performance from the inside out.
Right.
They didn't sacrifice conductivity for stability or vice versa. They got both by getting the molecules to work together and forcing the crystal to align.
And this raises an incredibly important question for materials science as a whole. It provides a brand new blueprint.
Yeah.
The concept of utilizing isomeric hydrogen bonding at interfaces and within crystals to guide orientation and stop degradation could be applied to so many other fields.
Like what?
Well, it could be used to stabilize highly efficient next-generation solar cells,
Yep.
create more sensitive advanced sensors, and potentially even stabilize quantum computing materials that are notoriously fragile.
Oh, wow. Quantum computing, too. Which perfectly brings us to our summary. If we look at the key takeaways from this deep dive into the Nature paper first, creating high-energy blue light usually requires intense electrical forces that rip apart fragile semiconductor materials.
Right.
Second, early workarounds like shrinking the materials to quantum dots failed because the required protective coatings ruined their ability to conduct electricity.
Exactly.
And third, the breakthrough came by introducing chemical twins that reached across the material boundaries, formed a network of hydrogen bonds, and locked the crystal in place while forcing it to grow into a perfectly straight, highly conductive highway.
Which is just a brilliant solution.
It is. This skyrocketed efficiency from under 6% to 22% and increased the lifespan 13-fold.
It leaves us with a really beautiful insight about the nature of human understanding and innovation, honestly.
Yeah.
Science isn't always about brute force or completely abandoning a fragile material for something harder or more rigid.
I love that.
Sometimes, the most elegant solution is simply about teaching an existing, fragile material how to hold hands, support itself, and stand up straight.
That is perfectly said. And that leaves us with a final provocative thought for you to mull over today as you go about your week. If scientists can manipulate invisible molecular hydrogen bonds to force chaotic, fragile crystals into perfect, stable alignments just to create a bright blue pixel on a TV screen. What other incredibly fragile, unstable materials in cutting-edge medicine or renewable energy could we revolutionize using this exact same molecular scaffolding?
That's a really exciting question.
The blueprint is out there now. We just have to see where it gets built next. Thank you for joining us in Deep Dive Lab today. If you enjoyed this journey into the atomic world of light and technology, be sure to follow and subscribe for more fascinating science stories. We will catch you on the next Deep Dive.